All right, well, welcome everybody. This is our this Open Research Institute, and this is our usual time slot for talking about field programmable gate array projects. And today we have a sort of a special presentation. We wanted to investigate and look into artificial intelligence and machine learning role in RTL design generation. And so, in coordination with the Information Theory Society, IEEE, and the IEEE local group Open Source Digital Radio, we put this together to promote and cross-list it. So thank you to everybody for helping make this happen. Okay, so where do we start? What are we going to try to do today? We're going to identify and discuss the core concepts for doing, RTL design with AI ML. And we're doing this from an open source perspective. So we'll talk a lot about open source from an open source point of view and integrate that into the discussion. We'll discuss a few selected works or groups of works, some papers and things like that. And then we're going to try to make some recommendations on literature, tools, standards, frameworks, where we think the good directions to focus work might be.
All right, thanks. So my name's Matthew Wishick. I'm a digital design engineer, system architect. Been working on modem designs for decades now. So been through these processes a number of times and looking at with the AI revolution as it is, how can these tools be useful in the ADA process in terms of how we can leverage these to improve the design process and get better results with our activities with digital design to make it more efficient and less error prone and determining how we can leverage these tools. So in terms of core concepts, one of the key things here is this broad category of electronic design automation. And, just my definition here, I didn't look one up, but in summary, it's kind of, it's all computer-based tools and workflows and processes that are used to specify, implement, and verify electronic design. So specifically ASICs and FPGAs, but it's applicable to PCBs and modules, systems, and subsystems. I think I mentioned it later, but another thing here is just even requirements capturing system specifications as well. But this kind of focused more on the implementation, I'd say. So in terms of EDA, some of the core areas that we use EDA tools are RTL designs and simulating RTL designs, synthesizing them, and then as we move those RTLs into implementation in ASICs and FPGAs, we have placement and routing, and one of the key things in the implementation phase is closing timing as meeting the performance objectives, right? We're targeting particular clock rates. Are we meeting those? And if we're not, that's a pain point, if you will. Another thing here that's important is to understand what are the risks, right? So when we're developing digital systems, we really see that there's three types of risks in the development of systems. The first is schedule risk. So we've set schedules and say we're going to accomplish various milestones at certain points, give dates into them, lines in the sand. And, we sometimes misestimate and things take longer than we intended. This is kind of the norm. I've only maybe worked on one project that came in on schedule over my, many years of doing this. And so, that's it creates problems like if you're trying to meet, customer deadlines or, get product available for, various activities. Like we had hoped at one point that the MSK modem we've been working on would fly on the sounding rocket this last summer, and we were far from meeting that hope. But that's fine. Sometimes schedule risk is is part of the game. And then the next risk is technical risk. And that's basically, we are saying, for example, we're trying to meet a 500 megahertz clock, but we're only able to achieve 400 megahertz. And maybe the design won't meet requirements at 400 megahertz. That really has to meet 500. And so that's a significant risk. You don't always know at the beginning of a project that these risks are achievable, or these targets are achievable. So that's a technical risk, whether or not we can actually do what we're trying to do. And then the third thing is just cost risks. And this is mainly, there's a lot of areas here, or this covers a lot of different things, but one of the key or good examples of cost risk is that we've underestimated the area. And so that requires a larger FPGA, which is more cost, or it requires a larger die. And again, that's more cost. So, these are the things that we always want to mitigate these risks as we're doing design processes. And so, this is kind of one of the areas that AI potentially can really help us with, is mitigating these risks. So if we can improve the processes, we can potentially mitigate schedule risk and technical risk, and even cost risk. So let's go to the next slide. So, one of the things with the design process is it's inherently iterative. We design something and then we go and simulate it, and we find problems, and so we go back and fix the design, and then we simulate it again, and then it's good, and then we go to synthesis and we synthesize it, and we find issues in the synthesis. Then we go back to the design, update that, simulate it again, synthesize it again, and now we're good. And then we take it to implementation, and we go to place and route, and we don't close timing. And so now we have to go back to the design. We tweak the design so that we can improve timing, maybe have pipeline delays, that sort of thing. And then we have to simulate it again, synthesize it, place and route, and maybe it still doesn't meet timing. So as we are finding problems later in this design process, they're more painful because the iteration loop is much larger, and it takes longer to go back to the beginning and work through that process again. So this is one of the key areas. If we can improve that, reduce the iterations. So let's see. So basically finding design deficiencies and identifying incorrect assumptions early in the design process. So I mentioned about the changing RTL to fix timing errors. That's a big iteration. The earlier you can find these issues, the better. So we can go to the next slide. So if we look at the FPGA design process, we talked about, there's a specifications phase, there's a architecture and partitioning phase, there's a RTL design and verification phase, an implementation phase, and a system validation phase. So, I think that there's opportunities for AI and ML to help with these various phases. Sometimes, we talked about the technical risk or the schedule risk or even the cost risk. One of the key things is getting the system specifications right up front. And if you don't have the specifications right, then all the work that comes after is potentially wasted. And you always have this often in this process. You'll have a feature creep. So you're third of the way through the process, and you're like, oh, we need this new feature, and so that impacts schedule typically. So, getting the system specification right is really critical to the success of the entire project. And, we never, as human beings, never get anything right the first time, but, minimizing what we miss, is really important. So I think that there's opportunities here, in terms of requirements, collection of requirement specifications, especially standards research. I think that we could really benefit from this. In fact, one of the papers that I will talk about at the end, or that we can discuss, is the the all the 3PP specifications, and then there's a AI agent or bot that will help you um, look through and understand and pull information out of those specifications because they're so complex. There's so many of them. So I think that's a good example of something that can help in the system specification phase. As we go into system architecture and partitioning, there's a couple of key things here. One is, there's a high level synthesis paradigm, but it's really difficult to implement in practice because you have to you have to tell the tools how to take that high level design in C or System C or C++, whatever tool your language you're using, and help guide it into doing a reasonable RTL design. And that's a lot of work and effort, and you need somebody who's familiar with kind of both the high level design and the lower level RTL to kind of guide the tools in this. And so there's work being done for AI agents to help guide that process so that it becomes less burdensome for people and we get more get better results. And then along that lines is doing design space exploration. So how do we partition a design? How much goes in software? How much goes in hardware? And so these agents can also help us evaluate the architecture and partitioning so that we get a more optimized design approach. And then one of the other things that there's some papers discussing is how we can take a high level design and predict timing after we've done layout and route. And so goes back to when we get to the end of the process and there's timing problems and we have to go back to the beginning. Again, this is an example of how we can try to predict what our final design is going to be, or the result, the timing of that design, so that we can make adjustments at the beginning of the process to minimize that iteration. And then we come into the RTL design and verification phase where we need to write RTL. And so we might be able to leverage tools to help generate the RTL, especially boilerplate stuff, simple things that we can, as designers, leverage those tools to improve our efficiency and kind of take out some of the drudge work, if you will, or so that we can focus more on the where on the design, on novel designs or things that let us optimize a design for the particular use cases or requirements. And then I haven't seen much of verification, but there's some. I mean, there's some tools now that are helping, say, with formal verification and other types of verification. So I think there's a lot of opportunity here for maybe test generation. There's some papers related to UVM. So there's opportunities here. And then as we move into the synthesis and placement and routing and timing closure, if there's, especially like placement is so key to having a good timing closure. If you don't have good placement, you'll end up with long routes and having difficulty closing timing. So, placement algorithms are, kind of one of the core things of EDA tools is getting good placements. And, there's work now in with AI agents to help that assist the placement process. Because right now they're algorithms, but sometimes as human beings, we can look and say, those placements are really bad. If we move this here, or we move that over there, or if we help, do some floor planning, we can see much better results. So if we can get AI agents to look at that floor plan and help guide that, then it becomes a more efficient process, and hopefully you would get better results in your timing closure. And which would also reduce area, because a lot of times if you have poor placement, and high fan outs, you'll add gates to mitigate these issues. And again, so that increases area. So there's a lot of things playing against each other here. And then the last phase is system validation. And so again, we spend a lot of time determining tests that we can take into the lab and validate the design against all the system requirements. And so, test automation, test generation is, again, a significant effort that we likely can benefit from AI assistance.
So the one of the selected works that we're looking at is a recommendations and roadmap for open source EDA in Europe. And this was brought to us by one of our community members, Thomas Perry, who was involved with helping write this document. And you can find the document at the link here in the slides. There are some assumptions that the stipulations that this work lays out. And the first one is that access to EDA software is traditionally very limited and costly. These are expensive tools, and the installation of these tools can require some pretty hefty hardware. Uh, so limited access. There is a workforce shortage with people that know how to use these tools really well and get things done. So collaboration and innovation and lowered barriers to entry, those are the things that are desired. And can they be achieved with an open source approach? And we bring an additional question: can they be achieved with AI ML? Can it help improve collaboration, innovation, lower barriers to entry, improve the workforce readiness? And we have seen some examples of open source helping EDA, and starting in 2015, the open source design intellectual property scene got a big boost from the RISC-V processor. That is still unfolding and advancing. You can see the impact from an open source IP design. An open source process design kit, or particularly PDK, for Google Skywater came out in 2020. And this targeted 130 nanometer process. So not exactly cutting edge, but this was a big deal and has made a significant impact. So we can see the effect of some open source frameworks and tools and intellectual property. Also, accessible manufacturing capacity. So, we can talk about tools and design kits and IP, but when we actually went to turn the math into molecules, that's a big bottleneck too. But we have seen some accessible manufacturing capacity come about because of open source work from, for example, the Open Road project at UCSD. So this affects the manufacturing capacity as well as EDA tools, open source EDA tools. So in this document, it describes, walks through a lot of content, but when it comes down to the recommendations that are made, the technical areas of focus that involve, the recommendations are, hey, pay more attention to this, that funding and mobilization of people needs to go towards these particular areas. And it's open source analog and mixed signal designs. And that's a highlighted area where I think a large amount of gain for the effort can be made. Interoperability and verification, that's a big technical area that needs attention. And getting more progress on the system on chip side of things. So we can see that there are some advancements from individual chunks of IP, but to do a system on chip, that requires a lot more integration. And there was a number of non-technical recommendations made to really kind of like clean up the license side. So when we talk about open source, and definitely when we talk about AI ML, that we need to make sure that what we're using and doing is owned, licensed properly. And for open source licensing, that means using an OSI, or Open Source Initiative approved license. So that's the sort of the standards body for open source licenses. And the big recommendation made was to pay more attention to that. That simply posting it in the public, saying that it's public domain is not quite good enough. You do need to go the extra mile and make sure that the stuff's properly licensed. Funding access, funding and being able to afford things is kind of a big deal. That's a non-technical area, recommended to focus more on funding. And the sustainability of projects. When you talk about open source and AI ML, sustainability is a big factor in both of these categories. when you have an open source project and it's can be a very decentralized group of people. A lot of them may be volunteering their time. If you suddenly lose part of the group or all of the group, or people decide that they're done and go on to bigger and better things, you can lose a lot of momentum. You can lose, in worst case, you can lose the actual progress, or the knowledge on how to do the different steps. Sustainability in AI/ML can be, it also is affected by essentially the same mechanism. If the person that owns the data set, that knows how to operate your data set, that knows how to train the model, that has done all of this training, leaves your company, and all of a sudden you have no access, or there's no documentation on exactly what the model is doing, then the sustainability of using AI/ML in complicated processes is very negatively affected. So we have seen this happen in a couple of cases. Funding of tape outs is a big bottleneck. So we have seen some improvement here in both open source. The funding of tape outs from an AI/ML perspective is, can you get somebody to go ahead and take the risk on funding something that was AI/ML? So it's been a question that's come up. Industry training and academic education, that's always a factor here. That's been a workforce issue in the past for the EDA kind of ecosystem. And industry training and academic support remains a problem for both open source and AI/ML. And then the other area of recommendation was, hey, we need more conferences. We need more, there needs to be some sort of way to filter, to sort of get a handle on all of this flood of information, all of these new AI/ML models, all of this potential, and that we really need to kind of get our hands around it. So that was an area that was pointed out in this particular document. So the areas of open source silicon design can be broken down into your design IP, so preferably open source design IP. That's kind of what we're talking about. And then you have your open source EDA tools. And then you have your process design kits, so those are like board support packages for this whole process. And they're a really vital part. You cannot get things done without them. And this is a Venn diagram. You can consider all of these parts as separate projects, and we can see that happening. There is actually a lot of open source hardware design. Well, I say a lot because not a lot in comparison to the grand scheme of things, but a growing number of open source hardware design and hardware IP. It's really exciting. That's one of the things that we do at ORI. And there are examples of open source EDA tools, like OpenRoad, and then the open source PDKs. So this is good. We have this. Where does AI/ML fit into this? There are some examples of large language models or prefabricated, automated writing of HDL. And this would go into sort of the design IP category. And we have a little bit of experience with two subcategories. And one is MATLAB's HDL coder, which lets you take a Simulink model and convert it into HDL. So we have tried this a couple of times, and we now have some sort of recommendations. We can recommend that HDL coder does work to produce HDL, human readable HDL that is fairly high quality. It does what it's supposed to do. And the process lengthy. We're talking like 12 to 20 steps in MATLAB to get this toolbox to produce the code. But the big caveat with it is that you will not be doing a big bang type of design. You will not be taking your entire Simulink model for your communications function, feeding it all at once into HDL coder and getting out something that will fit. It will be human readable. It will probably work, but it won't fit because it will be more than likely it will be way too large. So the placement and routing part. And I think Matthew mentioned this as part of the process that, this is an iterative process to create these designs, and the decisions that you make at the very top dramatically affect everything below it. And so this is something we noticed right away. So the way around this is that you have to divide up your design, and essentially each individual block in Simulink needs to be then converted into HDL, and a person has to go in and then stitch it together. This creates code that behaves a lot better. And our other experience with it, actually, the person that was most involved with that is here. So Paul Williamson, we took a handwritten COBS decoder. So constant overhead byte stuffing is a protocol that helps you out with making your information a little more resilient. So we wrote that in VHDL because it's part of our one of our projects. Having COBS decoder was needed. And so after we did this, handwritten traditionally, sit down, a couple of people write some VHDL, we decided to try to let ChatGPT take a crack at it. Um, because there's relatively little VHDL out there published open source to train, we suspect that probably is the reason that it failed. So it was not able to give us even a very accurate interpretation of the published protocol. Um, Now, what we did find that was useful is that it could set up the interface, so the ports and all of that were correct, but pretty much everything in the middle was wrong. And so that's a pretty common experience when you're trying to use LLMs to help you generate code. And with more training data, with more examples of a particular language, it gets better. But for our case, for VHDL, not really uh, there yet. The other big area where we see so AI ML is deep learning hardware models exist. Some published data sets exist. And this really helps you with some aspects of some of the EDA tools and some aspects of the process design kits. So we are starting to see that. And I think Matthew has found a number of papers in his literature search that brought this up, and I found a few too. There isn't anything yet that we're seeing that handles the whole process, but we are seeing places where AI ML is informing the process when it's managed appropriately. So just like with the open source design IP, you can't just throw a model at your EDA tool or vice versa and expect for it to give you good results. And you do have to know a lot about the underlying thing. So it doesn't let a non-expert come in and just do magic. That does not exist yet. But it does let experts get some things done faster, or it may feel faster. It may also lead, like in the case of prefabbed HDL, these prefabricated HDL blocks from like your Simulink, you customize the block and it customizes it for you. These things are presented by MATLAB as being verified already. So they're already solid code that's been worked through by experts. So you're using building blocks that are customizable. So not quite AI or ML, but on the road to the same sort of automation. And you can see where a body of work like this could easily be used by a model to make decisions and to stitch things together. So if you wanted to take like MATLAB HDL coder and make an AI ML system that out of that, I think you definitely could. You would have to generate an awful lot of the small blocks of HDL code, and you would have to then train on that, and then you would have to, give the feedback. Part of the feedback and some of the parameters would have to be how successful it was with place and route if you wanted to go all the way through on that. So bright future, really. But as you can see, just there's little chunks that have been taken out of this process. There's no magic here or anything that is completely solving the entire process for us. I asked people in our community and a few people like at UCSD and over in Europe and Fozzy, a couple of people on LinkedIn. So this is an informal survey of people that do this for a living. But I asked if could they please compare these 5 categories of, does it lower cost? What's the perceived quality, the learning curve, how agile you could be, and whether or not it expanded the workforce between open source AI ML and the sort of the traditional proprietary approach. And it was pretty interesting that the open source and AI ML kind of lined up with open source getting a little higher sentiment values. Open source is perceived as lowering the cost by quite a bit. It's perceived as being collaborative, expanding the workforce, It's perceived as being very agile because, oh, you just go in and customize what you want. And we all know that that's a lot harder to do than just going in and customizing, but that's the perception and the expected value, and also the learning curve. The learning curve was high for open source, for AI ML, and for proprietary. So the learning curve doesn't really change when you start adding in these things, when you consider all these different ways of doing things. The big difference was in the perceived quality. There is a very large bias towards high quality from proprietary tools, and a scary kind of lower quality expected from AI ML. I was told about hallucinations, and we experienced, ChatGPT basically confidently delivering erroneous Cobb's decoder code. Even for a very simple design like that, or relatively simple design, it was very wrong. So the that's where it gets a big hit, is the perceived quality, is that you can get results generated, but then you have to go back in and study it yourself. You have to fix it yourself. And both open source and AIML suffered from that. So this was sort of the breakdown in the sentiment and the stereotypes and biases, and like going into using these tools. That's kind of the lineup that developed. So again, this is an unscientific poll from a fairly small number of people, but they all were from all over the country, the United States and Europe. Um, and there was a fairly tight variance. So they all largely agreed in these directions. This is sort of the average of, please give it to me from a 0 to 100, uh, this particular score. Now, there's a large number of selected papers in AIML for EDA, or AI for EDA. That's the page name. This is a collection done by GitHub. So filtered list, curated list, and those are all the different categories with multiple papers listed in them, and it looks like it's being updated. So it ranges from high level synthesis down to testing, and also includes some papers that go into the documentation of data sets, which is where it's at when it comes to AIML. You don't have good data, you don't have a good model. And getting good data sets from EDA, from essentially a proprietary scene, is no small feat. So getting open data sets that you can use to train models is a big deal. We have a similar challenge in just general wireless, where how do you get good data to make good decisions for wireless models, for radio models? How do you get good data from an urban environment to a suburban to a rural? It's a huge task. And so similar challenge in EDA. And then I turned it back over to Matthew here to talk about the papers that he's been looking at in his literature search in archive.
All right, thank you. So yeah, I just have a RSS feed from archive for a few different categories, and one of them is EDA related and AIML related. And so, these are some of the ones that are interesting on their face. I haven't been able to dig into these as much as I'd like yet. But in terms of various design categories for like RTL generation, there's these papers like RTL Squad, being a multi-agent based interpretable RTL design. We can generate RTL. And then there's, this is always an important, thing. We talk about schedule risk earlier, and technical risk. They kind of, in this case, go hand in hand. Hardware verification can be very time consuming, hardware resource intensive, as Michelle mentioned. And so, being able to accelerate hardware verification, is a really, kind of one of a keys to improving the design process. If you have multi-million, multi-billion gate designs, being able to accelerate the verification of those designs is critical. And then again, there's another, example here. So these are just examples of what looked like relevant papers. So multi-agent engine for automated RTL code generation. So, I'm not, I don't, these aren't necessarily, ready to go. These aren't, ready for prime time, but it shows and demonstrates that there's work being done on these things in the academic setting, and and one of the things I'm particularly interested in is, can we start in any way leveraging these things, especially in the ORI work, as a way to get experience with it, or experiment with it, see how these things are can be applied, and if they're really useful or not. And so then the next thing is related to design verification, automated universal RTL verification framework using LLMs. That sounds really interesting. Again, RTL verification is a critical piece, and can be a very time-consuming piece of the design process. Um, Test bench generation. Sometimes generating test benches is just a lot of work, and as much as writing RTL can be error prone, even writing test benches can be error prone. And so if having a tool that can generate the test bench is something, again, it's just another tool in the toolbox. It's something that the designer can use to optimize or leverage these things to get better results in the end. Um, and then formal verification is another important piece of the verification process, and then so there's work again here showing that there's efforts to apply large language models to formal verification. Um, and then I mentioned, or we talked a little bit about high level synthesis earlier. So again, high level synthesis is a very, it's powerful in that I can just write C code and simulate the C code and verify the C code meets the performance specifications. But then, traditionally you take that C code and then you have RTL designers implement it, and then you run vector matching between the C code and the RTL code, and and that way you verify the RTL. But if you could generate RTL automated from the C code, that gives you certainly a leg up. But it's a difficult, and it's not an exact science. It's very dependent on the C code, the unrolling loops, all these things that these software constructs that don't map well into hardware constructs that have to be bridged in by these tools or by people to guide the tools to do this. And then we talk mostly about digital design, but there's application now, or using these AI/ML tools to help with analog design, and so that's useful. With Michelle mentioned the mixed signal and analog design earlier, and so that's a useful something that could help out a lot. Um, for myself, I think about, I'm not an analog guy, but I might be able to do some analog stuff a little more effectively if I had a tool like this, because it reduces my need to go off and learn something potentially, although I may not be able to see all the pitfalls that it has. But if I'm experimenting or wanting to try something out, it in terms of learning and becoming familiar with new concepts, being able to experiment with a tool like this could really be a learning experience. So it's not just using it in hey, I'm getting something out of it that I can send to production, but it may be a good way to learn concepts, or be able to say, this theoretical thing concept, how does it really apply in practice, and be able to maybe bridge that theory to practice. Next slide, please. And so I mentioned about standards research earlier. And so this Chat 3 GPP, is a tool that can help, review and uh, query, these 3 GPP documents. I think there's a copy and paste error. I'm sorry, the accelerating hardware verification of graph models. That doesn't, that shouldn't be there. Um, there's beyond EDA. One of the things I just would thought I'd throw in here just for the um, kind of seeds of things. AIML is even being used not just as a EDA process, design process, but they're looking. It's being used as a signal processing process, right? So you can design DNN networks that will detect convolutional code. So you could have multi-convolutional codes in your system, and you say, well, which one is this data that's coming in? Which code is it coded with? And you can have these AIML um, uh, agents that are detecting that, and so that they're assisting in this actual signal processing process. So they're part of the hardware, they're part of the system, and are doing work as part of the hardware and part of the system. And similarly, uh, there's these successive interference cancellation diffusion models that will help for channel estimation and data detection. So again, you're using these models as part of the system uh, design, part of the elements within the actual system. And then the last one here that I was also thought was interesting is using the LLMs for radio map generation. So what's the coverage of a cell network? And when you're planning networks, using these tools for um, understanding what the network needs to look like, how what coverage you're going to get. So these are kind of more system level, very high level tools. But so there's not just within EDA, but there's a lot of activity here in using these models as part of a system and part of, again, system planning. Um, so I don't I think that was the last slide.
I have I'd like to point out that the coding section here,
Mm-hmm.
there's a large overlap with information theory because the AI ML models that are showing promise approach it from like an information flow point of view. So if you
Mm-hmm.
track the level of entropy in codes or signals, that's turning out to be a big area of research and showing some real promise. And I think that there will be some work presented here in San Diego at the Information Theory and Applications Conference coming up in a few weeks. So that's a real good place to kind of look for this early work because that conference likes to showcase early work. And they're as dating as far back as 2019, which seems quite a while ago, in the final category for like radio map generation, wireless network planning, and also for dynamic spectrum sharing, that there's been some really interesting technology demonstrations. In 2019, it was DARPA, so they had a spectrum grand challenge, and they showed that yes, you could actually get more bits through some spectrum than you could just using uh, existing protocols, existing channels. And so that was the goal of that technology demonstration was to show that AI/ML could actually succeed in that area, which it did. And we've spent the all the years since then trying to make good on that technology demonstration. And it's still definitely a work in progress with AI/ML models. And again, it boils down to the quality of the data set. So yeah, let's see. I'll turn off the sharing. That's our last slide, and let's open up the floor to discussion and questions uh, and sharing of anything in this on this subject. I think both Ken and Paul probably have some some perspective here, Ken has been involved in ASIC design for a long time and may have some opinions on AI/ML helping with ASIC design implementation. And then Paul was the one that looked at using essentially large language model to help rewrite or to in parallel to look at a comparison with the Cobb's decoder work.
Yeah, as far as RTL development, I see a lot of C code being auto-generated from AI. And in principle, I don't see why that couldn't also apply to Verilog or VHDL. And I have heard of, I don't know the details. I've been trying to use AI channel estimation for some of the newer modem designs of 5G and beyond. I can just sort of confirm that I know that's an active area in industry, but yeah.
So it would be
Yeah, it would.
like better channel estimation in order to inform the design. Is that what you mean?
I heard reference to interference cancellation. I mean, that would be a way to, you could incorporate as part of an interference cancellation scheme. You could, I think in general, there's just certain patterns that machines can pick up on in terms of fading, particular fading scenarios, and it looks like this, or every time I drive this route, I get a particular. You can kind of anticipate
Yeah, I
the
was
channel
going to
conditions. Yeah.
add, if I might, like MIMO decoding, you need good channel state information, and so I think what you're talking about, and I see a lot in like 6G papers, is a lot of MIMO discussion and using AI/ML for channel state estimation so that you can improve the MIMO decoding because you
Yeah.
need good state information for MIMO decoding.
I'm reminded of the cognitive radio model when you talk about like routes that you drive a lot, that the so it sounds like you're talking about not just having better radio channel models in general, but specific models about where that person with that radio frequently goes, and that the radio learns. Like if they're in an urban environment and they generally have to, you generally have those sorts of channels and a particular set of interferers that it'll learn that and then modify the modem. So that's like an adaptive or cognitive radio model. That's pretty exciting. So Daniel, please go ahead. You have the floor.
Great. A question for you on that spider plot. You had you had proprietary solutions were preferred in one of the characteristics. What are some examples of proprietary solutions besides MATLAB?
Oh yeah, this would be the proprietary EDA tools. So all of the different tools in the ecosystem for electronic design automation. For I was pretty broad in the categorization. So there's people that had opinions about the like everything from Vivado, down to specific tools for place and route. So
Thank you.
that's sort of the category was sort of I tried to like meet people where they were and figure out their opinions, and it's not an uncontroversial sort of sort of chart because I think we've all had experiences with proprietary tools that had that were not totally great, So if you just got to go on the Xilinx or now AMD, so go on their forums and see the number of like reported bugs in Vivado that have been there for a very long time and are very annoying. And so, but people view these as safe because they have a large staff of people paid to write and maintain these tools over now decades. And so it's very difficult to kind of overcome a bias or a stereotype that this is quality, this works, yes, it might be hard to use and documentation. There might even be too much documentation, like say, a user guide that's 1,500 pages long sometimes is not as helpful as it would be if it was shorter, and better indexed. But yeah, that's kind of the lay of the land in that category.
If I can add there, if just from personal experience, um, you know, using open source simulators versus proprietary. I mean, whatever problems you might have with your Questasim simulator, um, I can get more done with that more effectively than I can with open source simulators, right? So, in particular, like on the MSK development that we've been doing, I've been using we did a VHDL implementation and using GHDL simulators and the NVC simulator, but there's some potential need to include some Verilog pieces, and there's no cross-language open source simulators available. So it makes it really difficult to do a multi-language simulation with open source tools. It's just it might be possible using foreign function interfaces, but then there's a lot of effort that goes into trying to kind of stitch these tools together, and then it's not going to be perfect. And so I think in terms of quality, it's something that works versus something that, because you have a lot of people and big budgets developing it, versus, just some really good open source simulators, but just don't have the feature set parity that allows people to be, as productive as they can be with the proprietary tools.
If I could do a follow-up question to that, I don't know if that indicates that this might not be a good target for open source. That would be the automatic generation, because if the commercial entities, highly staffed and heavily expensive, paid to troubleshoot bugs, can't keep on top of that, an open source community is notorious for having great difficulty in correcting bugs. Now, maybe a counterexample of what I just said would be the Linux project, but there it's a total addressable market in the hundreds of millions of people, whereas the EDL design, what could be the total addressable market? Not nearly as big, I'm certain.
Yeah, very
Well,
good. Those are very
yeah,
good points. And anytime that you're looking at an open source project, it can be a personal interest, and we see this a lot, that there's lots and lots of open source projects that are personal projects. There's something missing, and somebody has the time and the energy to go and write it. So that's a very long tail in a very large distribution. On the other end are these very large open source projects that do meet all the requirements and do consistently deliver good results. And Linux is probably the best known. Apache, things like that. The vast majority of internet infrastructure all runs on open source code and generally works pretty well. But the your point about the market size is a big driver. So a big complex project like open source EDA tools does not come about with purely by a bunch of volunteers getting together and deciding that'd be super fun to do. The Open Road project, for instance, is a big formal project with multiple layers of funding and is at a university. So this is a sort of, if there was like a pro category of open source, it would fit into that. And they have specific goals. They want to achieve, this the subsection of all the requirements that proprietary tools do, and then continue to kind of work their way up the chain to deliver things. And like Matthew said, language coverage. That's one of the big ones, so big drawbacks of like doing any sort of open source technical project like this, because we can see it in Amaranth, which is a really neat project that takes Python and turns that into HDL, or gets you closer. So sort of like an HLS attempt, but Amaranth picks out particular things and does those particular things well, and then the rest is either left as an exercise to the reader or will be done in the future. So we see that pattern. And, so committing to open source just blindly or as a category, that means that you have these, fairly deep chasms of nothing. And as long as you're willing to accept that, then sure, you can, or you can take a more pragmatic approach and say, we are going to produce open source work. Our particular IP or our particular design or tool is going to be open source, but you use whatever you need to use the best tool for the job in order to get that end goal across the line. And you can see that there's a cultural difference here. You can be a purist and reject proprietary anything along the way, or you can use whatever tools you have to produce your end product being open source. So we fall generally into that second category. Use anything that we need to use along the way, and then the end result is unquestionably, open source. And so that's kind of, I think, for tools like the point you're raising is exactly right. I don't want to guess, but yeah, I think the market for EDA tools is a whole lot smaller than Linux. And that makes a big difference. When you don't have a huge market of people, you get less feedback. Um, you get less, of a lot of things. And you might be able to score some funding if it's economically important. And EDA tools have been identified as very economically important, and more so since like the CHIPS Act. So we can see that there are sources of funding, but that still not having a huge audience or market is a big factor in getting the necessary feedback and also the necessary volunteers, or even paid people to execute the work.
Maybe countering my own assertion is that it'll just take longer to come up with the open source solution. A lot of things benefit to work toward that. AI tools will become better, making the problem easier to solve, and more time, of course, helps in finally getting development done. That's my assumption. So I'm very hopeful.
Yeah, if I may, I think those are good points. And the EDA market is incredibly small, which is one of the reasons the tools cost so much, because they have to amortize them over a very small, set of customers. But back in the early '90s, when Synopsys was relatively new on the scene in terms of synthesis, spent a lot of time going, just wish the Synopsys engineers would use their tool, because it could be really frustrating. But it makes me now think about it's a special, unique engineer that can know software well enough and hardware well enough that they can create these tools, right? So I mean, I think that's maybe part of the problem is it's a very unique and small number of individuals that can really understand the software side and the hardware side so that they can create these tools that are really effective. And so I think a lot of them end up working for the EDA companies in the first place. So there's not a lot of availability, I mean, I think there's some really good open source projects, GHDL, NVC, Verilator, iVerilog. These are all really good projects, but they're not, I would say, comprehensive, right? But then there's some other really good, I think, examples like KiCad for schematic and PCB design. That's a really well supported project. You could do, commercial designs with that easily, where it might be harder for an FPGA or ASIC design to use, these open source simulators. So, I mean, yeah, I think there's a lot of opportunity, but it is not a simple problem. And but maybe if we can, raise it up, and get more people interested, it might be something that, we can contribute more to some of the tools and in the development of those tools, or maybe, if there's grant opportunities to help, encourage development, there might be ways we can help these developers bridge some of these gaps, maybe.
Great. I'll be looking forward.
Yeah, the nice thing about open source projects, if an individual can get hooked up with the right one, is that it's a very powerful way to get some professional development, like experience doing something that can then help you in your career or educational path. And so that's one of Open Research Institute's missions. That's one of the reasons we're here, is to let people get some experience in design and and be able to move forward with their technical expertise. And the kind of the cost of this is that, you do have people that will show up and volunteer and then they get a better job, or they get into a master's program or get into that PhD program, and you won't see them again for a while. So there is a sort of a different pattern to the efforts. So that we really try to promote open source as a way for you to get, personal and professional and educational advancement. So your advancement doesn't come after you get the job. And in the EDA world, these are not very many jobs and only a few companies. So it's a chicken and egg problem. How do you get good enough to do this work and to really contribute, if that's your vocation, if that's your calling? Um, without getting hired, and you can't get hired unless you've demonstrated some mastery in this field. So both AI, ML, and open source are ways to kind of improve that. So there's a lot of attention paid, especially within IEEE, for workforce development, especially in semiconductors and all of the related fields. And so, what we're talking about today is a part of that. I think AI ML has a whole lot to offer, and being successfully incorporated with open source is from what we can tell, is going to give a lot of gain. It'll give a lot of bang for the buck. All right, any other questions? All right, Matthew, you have the last word.
Thanks. I'm really excited about the opportunities here. I mean, I've been, the digital designer, system architect for many, many years now. And, I think this is a new evolution. When I started out, I was still interacting with engineers that did ASICs with schematics. But HDLs were coming on the scene, and, those engineers kind of, if they didn't move on, they were, they became obsolete. And so one of my goals here is, not, just even for myself personally, to grow and continue learning and building skills and finding ways that, new opportunities here as AI/ML, becomes more and more pervasive, to understand how these tools can be leveraged and used in doing these designs. So I think it's interesting, useful from a general perspective, and but even from a personal perspective, that there's still a lot to learn and grow. So I'm excited about that, and I appreciate these discussions, because they're I think the foundation, the collaborative nature is really, what I found over my career is really beneficial, and helps grow and learn and be successful. So I appreciate this organization for that, and being able to engage in these discussions. I hope there's many more to come, and that we see a lot of interesting things come out of this.
Yeah, I think that's a great thing to pick up on, because what we'd like to do is to look at all the things we talked about today, all of these many, developing frameworks and resources and libraries and all of that. Just the list, just from the archive list from that Matthew gave, is immense. It's a lot. It'd be really good to pick something and then give it a shot, to go ahead and try it out, and then come back and have another meetup about it. And so I think that's what we'll try to do next, is to try to pick something and explore it, and then we'll be able to give a report about how it went, like first person experience with it, on open source designs. And this gives a lot of visibility to the sort of what happens when you go from, hey, this looks like it'll work, or it has lots of promise, to, well, we tried it and here's where it worked and here's where it didn't. Similar to our experiences actually trying to use HDL Coder in MATLAB. It was very informative and some useful when you use it the right way. So that sort of thing, spreading the word on that would probably be of interest to a lot of folks. So stay tuned. We will work together with Open Source Digital Radio Group in San Diego and the Information Theory Society. And we also have had interest from the Consumer Technology Society, the local chapter here in San Diego. So we're going to spread the word. Computer Society probably will be interested in hearing about experiences with particular frameworks and models. So we'll definitely continue it. And thank you, everybody, so much for sharing your part of your day with us. Your time once spent, you can't get it back, so we consider it to be pretty priceless. And yeah, appreciated. And what we'll do is we'll distribute the slides to everybody that's registered and send you the link to the recording. And yeah, if you have any follow-up questions, please let us know. And we'll see you again soon.